Hi, I'm Yeshwanth, and I'm going to be presenting our paper, Terminal Embeddings in Sublinear Time. And this is joint work with Jelani Nelson at UC Berkeley. We're going to start with the concept of a metric embedding. Here we have two metric spaces, H and J, with some privileged subset X of H. And we say that F is an epsilon distance preserving embedding from H to J if for any pair of points in the privileged set X, F approximately preserves the distances between that pair of points in the embedding space. And here epsilon is going to measure the degree to which F actually preserves these distances. In this talk, we are going to focus exclusively on the Euclidean dimensionality reduction version of this problem, where both the metric spaces are finite dimensional Euclidean metric spaces. And typically, the embedding space J is going to be of much smaller dimension, K, compared to the original high dimensional space X, high dimensional space H. And X is going to be some finite subset of H. So in this talk, we're going to use D to denote the dimension of the original space. And we're going to use K to denote the dimension of the embedding space. So what's known for this problem? A classic construction that dates back to Johnson and Lindenstraus shows that if one picks F to be a random linear embedding, this embedding is going to be a valid epsilon distance preserving embedding, as long as the dimension of the embedding space is at least log n over epsilon squared. Subsequent work by Larson and Nelson has established that this embedding dimension is optimal up to constant factors. So you can't really do better than log n over epsilon squared. And one typical application of these kinds of techniques is in reducing the dimensionality of search problems. So suppose one was interested in a search problem like nearest neighbor search. You could then use this technique to execute this search in a lower dimensional space as opposed to the original high dimensional space, possibly giving speed ups in complexity. However, one downside to these techniques is that they require X, the privileged set, to be chosen independently of the embedding matrix phi. And this could be a problem in scenarios where the specific query that, let's say, your nearest neighbor search algorithm witnesses is somehow dependent on previous queries made to your data structure. So this breaks this independence with the definition of the embedding matrix, and this could in turn lead to incorrect results. So is there some way for us to weaken this constraint or to lessen the effect of this form of dependence? And one way of doing that is to strengthen the second constraint. Not only do you now want to preserve distances between pairs of points in X, but you also want to preserve distances from any other point in RD to any point in X. So in the earlier definition, we could only preserve distances between pairs X and Y, both from capital X. But now you let Y to be any point in RD. In this setting, one can show that linear embeddings provably fail. So in particular, one could simply pick Y to be orthogonal to the rows of the embedding matrix, in which case the embedding would not resolve points that could be arbitrarily far away in the null space of phi. However, these embeddings are known to exist. Elkin, Filser, and Neyman constructed an embedding for constant distortion, for constant epsilon. This construction was further expanded to arbitrary distortion, but with a suboptimal embedding dimension of log n over epsilon to the 4 in work by Mahmadi, Makarichev, and Rajenstein in 2018. And finally, this construction was shown to have the optimal embedding dimension of log n over epsilon squared in this paper by Narayanan and Nelson in 2019. One downside to all of these approaches is that they are slow to compute. And in particular, all of them run in slow polynomial time because the construction of the embedding is defined in terms of a semi-definite program. So in our work, we want to construct a data structure which computes terminal embeddings faster than these previous approaches. And our main result is that we construct a data structure, which when instantiated with the set X, and then later queried with any query Q in RD, constructs a valid terminal embedding for Q in sublinear time. And the precise speed of this embedding time follows a trade-off between the space occupied by the data structure and the amount of so the precise amount of time taken by a data structure to compute the embedding depends on the amount of space available to it. And a few concrete instantiations of this trade-off are illustrated in this table. So suppose we were in the regime of near linear space. So suppose we had approximately ND amount of space, which is the amount of space needed to represent the privilege set X. Our data structure gives an embedding time of n to the 1 minus c times epsilon squared. However, if we allowed space that was quadratic in n, the embedding time improves to n to the 1 minus c epsilon. And if we had a much larger amount of space, so a space complexity scaling at n to the c over epsilon squared, our embedding time is nearly independent in the size of the privilege set. Before describing our data structure, I'm going to overview previous constructions of terminal embeddings. In the first step, you simply draw a standard Johnson-Lindenstrauss embedding. So you draw a random linear K by D matrix. Sorry, you draw a random K by D matrix. And for any point in the privilege set, its embedding is simply going to be the linear embedding with respect to the Johnson-Lindenstrauss sketch, augmented with an extra coordinate, which is set to 0. And now, suppose you witness a query Q in RD, and you want to construct a terminal embedding for Q. First, you're going to find the exact nearest neighbor, to Q in the privilege set X. And now you want to find a vector U in the embedding space which satisfies the following angle constraints. For any point in the dataset, you want the angle between U and the embedding of that point to be approximately equal to the angle between Q and that point. One more important thing to note is that these angles are going to be measured with respect to the nearest neighbor, X star. So the angle between Q and X1 is going to be approximately equal to the angle between U and Fx1, measured relative to the nearest neighbor and the embedding of the nearest neighbor. And a simple extension of any U star which satisfies these constraints can then be shown to be a valid terminal embedding for Q. Now we're going to formalize the previous requirements into this program. So we're going to have two constraints. The first constraint is the distance of U from the embedding of X star is going to be less than the distance of Q to X star. And the second is the angle constraint rephrased in terms of an inner product. So what we're going to enforce is that the angle between U and the embedding of any point X is going to be approximately equal to the angle between Q and that point X measured relative to the nearest neighbor and the projection of the nearest neighbor X star. And we're going to extend a solution to this program U star as before. And the previous work has shown that when K is chosen to be approximately log n over epsilon squared, the program is both feasible for any query, and the extension satisfies the required distance preserving constraints. So now, how do we solve this convex program quickly? So we're going to make a few observations. The first observation is that this program is low dimensional. Recall that we're searching for a vector U in the embedding space, which is just log n over epsilon squared. So the problem itself is a low dimensional problem. And Because of that, a small number of queries to a separating oracle to this set of constraints suffice to find a approximately satisfying point. Therefore, the main problem is in constructing a separating oracle to these set of constraints. The first constraint is easy enough to check. It's simply a distance check. So you simply check the distance of a candidate U to the projection at the nearest neighbor. The second constraint involves two-end linear constraints. And therefore, the main problem will boil down to whether we can check the second constraint effectively. To do this, we're going to work with a simple reformulation of the second constraint. Instead of having a difference between two inner products, we're going to group together the first two arguments, the first argument of each of the inner products and the second argument of each of the inner products into larger vectors VU and WX. And we're going to write the inner product constraint as the constraint that this one inner product between these augmented vectors is going to be small. Note that the first vector VU is the only vector that depends on the query and the candidate embedding, while the other set of vectors WX is completely independent of the query and its candidate embedding beyond just its dependence on X star. So the only thing you need to know is what the nearest neighbor is to define the second set of vectors WX. And furthermore, since pi is a distance preserving embedding for the points in the data set, WX, the vector that does not depend on U or Q, is of scale approximately √2. And when the first constraint is satisfied, when U is closer to the projection of X star than the distance of Q to X star, VU is small. Therefore, checking the above constraint effectively boils down to a nearest neighbor search problem. So if the inner product of VU with WX is very large, VU is going to be much closer to WX than it's supposed to be. On the other hand, if the inner product of VU with WX is very small, then VU is going to be much closer to minus WX than it is supposed to be. Whereas the constraint effectively enforces that both of them are approximately orthogonal. And because of this, we can effectively check this constraint using these augmented set of vectors WX using a nearest neighbor search algorithm. One thing to note is that this nearest neighbor algorithm needs to be adaptive because the precise query that it's going to get could be chosen with complete knowledge of how the data structure itself is constructed. The construction of these adaptive approximate nearest neighbor data structures follows largely from prior work, so I won't dwell on them here. But assuming that these data structures exist, this is how we build our data structure for constructing terminal embeddings. In the instantiation phase, we construct an approximate nearest neighbor data structure with the point set capital X. And for each candidate nearest neighbor X star, we're going to construct an approximate nearest neighbor data structure with the points WX being centered at X star. So for each X in the data set, we construct another approximate nearest neighbor data structure with the points at WX centered at that particular X star. And at query time, this is what we do. So we first input the query queue in RD, which could be chosen with knowledge of the data structure. We find its approximate nearest neighbor X star using another approximate nearest neighbor data structure. And finally, once we know what X star is, this is how we construct our separating oracle. We first check the first constraint. We first check that the candidate terminal embedding is not too far away from the projection of X star. And if it is not too far away, we can then query the corresponding nearest neighbor data structure with the data points WX. And this is guaranteed to run in sublinear time and gives us a sublinear time data structure for computing terminal embeddings. Unfortunately, the construction as it's just been described has two main drawbacks. The first is that it has large space complexity. Recall that for any candidate nearest neighbor X star, we construct another approximate nearest neighbor data structure with n points. And because of this, we construct at least n data structures with n points. Therefore, the total space complexity is at least n squared. And the second somewhat minor point is that the data structure or the embedding time of the data structure scales roughly as d times n to the row for some row less than 1. Whereas what you would ideally want to expect is a decoupling between the terms that depend on the dimension and the term that depends on the number of data points in the embedding set. It turns out that the second problem is not a significant issue, and it can be easily addressed. The first problem requires several further modifications to the approach that I've just described. And we're going to start by expanding the second set of constraints. Recall earlier that our inner product construction, our inner product constraints, only required us to satisfy the inner product constraint centered with respect to the true nearest neighbor X star. Whereas now we want to satisfy the inner product constraint for centered at any other point X in the data set. So our earlier construction only required us to satisfy this constraint when Y is the nearest neighbor X star. But now we will require it to hold true when Y is chosen to be any point in the data set. So this is somewhat paradoxically an even stronger constraint than the one we had before. A simple argument shows that even this multi-centered version of the second constraint remains feasible. So any solution to the set of constraints is also going to be extendable to a terminal embedding. However, our main observation is that despite the fact that we have more constraints now, n square as opposed to n constraints that we had previously, despite the fact that we have more constraints, we don't actually need our candidate U to satisfy all of them. We only need our candidate U to be extendable to be a valid terminal embedding for Q. And the key lemma that helps us exploit this fact is that for any point X in the data set, to ensure that U preserves distances to X, it suffices to check the inner product constraint for some centering point to Y, whose distance to X, or whose distance to Q is comparable to the distance of X to Q. And this provides us with a couple of avenues for improving the space complexity of our data structure. The first is that we could instantiate fewer approximate nearest neighbor data structures. So even let's say for the nearest neighbor X star, we only need to check this constraint for some Y, whose distance to the query is approximately equal to the distance of X star to the query. And the second way this can help us optimize the data structure is that we could use a fewer number of points in each data structure. So we don't use all n points for each one, but we just use a smaller subset. To precisely trade off between each of these options, we leverage constructions from locality sensitive hashing, which are previously being used for nearest neighbor search. I won't dwell anymore on how we use these data structures, but all the details are in the paper if you're interested in checking it out. And now I'll conclude with some open questions. Our constructions, because they rely on these locality sensitive hashing data structures, are only valid in the constant epsilon regime. And therefore, one open question could be construction of these faster data structures for computing terminal embeddings when epsilon decays in n. And the second open question is somehow a reversal of the first one. Our data structure can approximately be viewed as a reduction from the problem of constructing terminal embeddings to the problem of finding approximate nearest neighbors. Can we show that something is true in the reverse direction as well? So can we show that nearest neighbor search is approximately as hard as verifying whether a candidate point is an approximate terminal embedding? And a final open question is whether some of these adaptive embeddings are possible for other LP norms beyond just the Euclidean norm considered in our work and previous work. And with that, I'll conclude the talk. Thank you for listening.